Hello. This video is about L'Hopital's rule, which is a very particular method of evaluating certain very particular kinds of limits. The final two examples illustrate how we can extend L'Hopital in a couple of different directions. Suppose we want the limit as x goes to 0 of x times log x. Well, as x goes to 0, x goes to 0, and log x is going to minus infinity. So this is a 0 times infinity type situation. And again, we have these two elements in our limit that are pulling in two completely different directions, and we have to figure out who wins. But it's not 0 over 0, and it's not infinity over infinity. What do? Well, in this case, we can make it into an infinity over infinity form. And we replace the x log x by something that's algebraically equivalent, log x over 1 over x. So log x over 1 over x is the same function as x log x. But now it is we have an infinity over infinity form, and we can apply L'Hopital's rule. We get 1 over x for the numerator minus 1 over x squared for the denominator. And now we do a little bit of algebra on here, and that's equal to minus x. The limit of minus x as x goes to 0 is 0. So this initial limit up here, which was the limit as x goes to 0 of x times log x, that's equal to 0. There are two places here where I've made algebraic changes in the expression of the functions. And if you're not comfortable with those steps, you should pause this video until you are comfortable with what I've done there. I'm just doing things that you will have learned about in school. And so there's nothing mysterious about what's going on here. But if you don't see immediately what I've done, then you should make sure you understand it before you move on. It's a good example of the way we use algebra to simplify calculus expressions. Okay, the sixth and final example is the limit as x goes to 0 of x to the x. This appears to have a limit like 0 to the 0. And a 0 to the 0 is an indeterminate form because the base is trying to make this limit come out 0, because 0 raised to any power is 0. The exponent, though, is trying to make the answer be 1, because if you raise anything non-zero to the 0 power, you'll get 1. So we have an indeterminate form because the two elements in it are pulling in opposite directions, and there's no way for us to see immediately which factor is going to win. Now here we do something that's different. We're going to let y equal x to the x, so it's the limit of y as x goes to 0 that we're after. But we take the logarithm of y, and we'll take the limit as x goes to 0 of log y. And we do this because it will simplify our exponential expression here. So we take the limit as x goes to 0 of log y, and the logarithm of y is x log x. So we have the limit as x goes to 0 of x log x. But we just did that limit, and we discovered that it was 0. So the limit as x goes to 0 of x log x is 0. So that's how we get the limit of log y. But log y is equal to 0 if and only if y itself is 1. So saying that log y tends to 0 is the same as saying that y itself is tending to 1. So now we have the limit as x goes to 0 of x to the x is equal to 1. Okay, I just want to caution you that in the interests of avoiding circular reasoning, there are a few limits that look like you should apply L'Hopital's rule, but you should not apply L'Hopital's rule. If we have used a particular limit in our derivation, our proof of the derivative of a function, we cannot then use the derivative of that function in the L'Hopital's rule that we use to evaluate it. So for example, we use the limit as x goes to 0 of sine x over x equals 1 in order to prove that the derivative of sine x is cos x. So we can't use L'Hopital's rule to prove that this limit is equal to 1 by taking derivatives of sine x and x, because that would mean we are arguing in a circle. It's very clear when you look at this last example. Where have you seen this before? Well, that's the definition of the derivative of f evaluated at a. But it is an indeterminate form. As x goes to a, the numerator goes to 0 and the denominator goes to 0. It looks like it's begging to have L'Hopital's rule applied, but it won't, we can't, because if we use the derivative of the numerator, we'll be using f prime, and this is the definition of f prime. So we'll be using a derivative to evaluate itself. And that bit of circular reasoning is something where we really want to avoid doing in all of our mathematics. Let's conclude this video with a summary of L'Hopital's rule. L'Hopital's rule is a simple way to calculate limits in those cases where it actually applies. When you can use L'Hopital's rule, all you do is take your limit of f over g and evaluate instead the quotient of derivatives, f prime over g prime. And sometimes that is a simpler limit to do, and so you do that. And you can keep doing that, taking more derivatives, as long as each one of them is an indeterminate form until the one where you actually evaluate. We have to have exactly the right type of formula here. We have to have 0 over 0 or infinity over infinity, and we actually have to have a limit value for the derivative, the limit of f prime over g prime, before we can make that statement. We can use L'Hopital's rule in these cases when it's 0 over 0 or infinity over infinity. We can use it if the limit of f prime over g prime turns out to be plus infinity or minus infinity. That's fine. We just say that that's what the original limit actually was. And we can also take the a that's in here and make that a plus infinity or minus infinity. We can take limits as x gets goes to infinity or as x goes to minus infinity, and we can use it in those cases as well.